This is the first video for application of forces, and in this video we're going to start building on all the work you've done on mechanics so far. Okay, and in this series of videos we're going to start by looking at static equilibrium, which means that resultant forces and moments, if we have them, will be zero. So we're going to look at ladders, pulleys, beads on string, and rods or particles on an incline. So let's have a look at this first question. So you can see here it says, okay, a mass of 3 kilograms rests, I'm going to underline a few key things, 3 kilograms rests on the surface of a smooth plane, which is inclined at an angle of 45 degrees to the horizontal. The mass is attached to a cable which passes up the plane along the line of greatest slope and then passes over a smooth pulley. Now, remember, these are some of your modelling assumptions. Remember what we know about if a string passes over a smooth pulley. It's something to do with the tension in the string. The cable carries a mass of 1 kilogram freely, suspended on the other end. The masses are modelled as particles, again, think about your modelling assumptions, and the cable as a light inextensible string. So, in order to keep this system in equilibrium, okay, because if we just let it go, it would slip somewhere. We've got a force P acting horizontally on the 3 kilogram mass, keeping the system in equilibrium. And what we've got to do is calculate the magnitude of P and the normal reaction. Okay, so the first thing I'm going to do is I'm going to put some forces on this diagram. Okay. So I'm going to put the forces on in red. So I'm going to start with the 1 kilogram. So we've got a tension going up, and we have 1g, or just g, coming down. That's the weight. Remember, mass times gravity. Right, now we're going to look at the 3 kilogram. So the first thing I'm going to put on is I'm going to put the weight. So that's 3g. I'm going to put the normal reaction on, R. And there is a tension in the string attached to a 3 kilogram mass. Okay, so the first thing I'm going to do is I'm going to resolve any force that is on the slope that is not parallel or perpendicular. So I'm going to do that in green. And I'm going to start with the weight. Okay, so I'm going to resolve it. So I'm going to make it come down and across like that. So this is 45 degrees here. So the vertical component will be 3g cos 45, and the horizontal component will be 3g sine 45. Okay, now the next one I'm going to do is the force that's holding the system onto the slope, which is the P newtons. So we're going to resolve that. So again, go across and down this time. And of course this is 45 degrees using parallel lines. So the force that's going across will be P cos 45, and the force that's going down will be P sine 45. I'm just going to squeeze that in there. Okay, so I'm now going to shrink that back down again. Okay, so you can see it really quite well. Right, so we're now going to do some resolving of forces. Okay, so the first one I'm going to look at is the 1 kilogram system, this one here. I'm going to look at this one. And you can see, remember, it's going nowhere, it's in equilibrium, so up equals down. So therefore, T must equal G. Right, so that's for the 1 kilogram force. You can actually label it up if you want to, signpost it. Okay, so let's look at the 3 kilogram. And for the 3 kilogram, we're going to do first thing I'm going to do, sorry, for the 3 kilogram, is we're going to look up the slope equals down the slope. So the forces that are going up the slope is T and P cos 45, and the one that's going down the slope is 3G sine 45. Okay. Now, we already know that T equals G from the 1 kilogram mass, so therefore G plus P cos 45 equals 3G sine 45. We only have one unknown in that, so I'm going to rearrange it to get P on its own. So therefore P will equal, so it's 3G sine 45 minus G divided by cos 45. If you pop that in your calculator, you'll find out that P is 15.54 newtons. Okay, or more likely, better than that, of course, because G is 9.8, you can have 15.5 or 16 newtons. So remember, when you are using G as 9.8, your answer must be to 2 or at the most 3 significant figures. But I'm just going to keep the 15.54 because the next bit asks us for the normal reaction. So this time I'm going to resolve up from the slope and down from the slope, so perpendicular to the slope. So if you just have a look now, you can see that we've got R, and that's the force that's going up perpendicular from the slope, and coming down we've got P sine 45 and 3G cos 45. And of course, if you put in your P from the other part and use your calculator, you find out that R is 31.77, therefore is 31.8 newtons or 32 newtons, again maximum 2 or 3 significant figures. Right, the next thing we're going to talk about is beading and beads threaded on a string. Now, there are 2 situations that you could get at A level. Situation number 1, this one, is where you have a smooth bead and it's threaded on a single string. Now, because it's a smooth bead, the tension on either side of the string, or the tension on either side of the bead, will be the same because it's a smooth bead. It's very similar to using a smooth pulley. The other situation, this one, is where your bead is attached to 2 strings. So it's actually tied to 2 strings. Now, in this case, depending on the situation, the tension could be different in both of the strings. So we're just going to have a little look at 2 questions. Okay, so this one, we have a smooth bead, quite important, is threaded on a light inextensible string. Okay, the ends of the string are attached to 2 fixed points X and Z on the same horizontal level. The bead is held in equilibrium by a horizontal force of magnitude 8 acting parallel to ZX. The bead Y is vertically below X with angle XYZ 30 degrees. We need to find the tension in the string and the weight of the bead. So the first thing we're going to do is we're going to put our forces on. I'm going to put those on here. Okay, so we've got tension in the string, and remember it's passing through a smooth bead, so that those 2 T's will be the same. And we've got weight, and we've got the 8 Newton force. Now you can see all I need to do is resolve the tension. So I'm going to do that in red, and I'm going to resolve the tension that is not acting vertically or horizontally. So I'll do a cross and up. Okay, so remember this will be 30 degrees, so this is T cos 30 and T sine 30, and the arrows indicate the direction in which they're going. So what I'm now going to do is I'm going to do some resolving. Balancing. So the first thing I'm going to do is I'm going to do left equals right. So what are we going left? We've got 8, and right is T cos 30. Okay, so therefore T will equal 8 over cos 30. Therefore T equals 16 root 3 over 3. T therefore is 9.24 newtons to 3 significant figures. And again, because I've not used G in that calculation, I can do it to 3 significant figures. Now, if we balance the forces, up equals down, you can see that the forces going up is T plus T sine 30, and that equals W, which is my weight. And I'm going to, again, use as accurate answer as I can. Don't forget, in first part we knew that T was 16 root 3 over 3, so I'm going to substitute that into those 2 places, pop that in my calculator, and I get that W is 8 root 3, or W is 13.9 newtons, again to 3 significant figures. Okay, so that's the situation we've got where we have a single string that's threaded through the bead. This question, okay, and again, I'm going to put some forces on. It said a particle of mass 6 kilograms hangs in equilibrium, suspended by 2 light inextensible strings. Okay, inclined at 60 degrees and 45 degrees, as shown in the diagram. We want to find the tension in each string. That's what we're trying to do. Right, so what I'm going to do, again, I'm going to zoom in on the diagram and just put some forces on. So we've got, I'm going to call the tension in the left string T1, the tension in the right string T2, and we've also got 6G as our weight. I'm now going to resolve the 2 tensions because they are the ones that aren't acting vertically and horizontally. So T2, I'm going to resolve it like this. This is 45 degrees. So this will be T2 cos 45 and T2 sine 45. And likewise with T1, I'm going across to the left and up. Again, this will be 60 degrees. So this is T1 cos 60 and T1 sine 60. Okay. Right, I'm going to shrink that back down again. Okay, so what we're going to do now is we're just going to do some balanced forces. So the first thing I'm going to do, I'm going to do left equals right. So based on my diagram, I have T1 cos 60 equals T2 cos 45. Okay, now if you pop that in your calculator, you see you've got half T1 equals root 2 over 2 T2. Okay, right, now I'm going to do up equals down. So we've got going up, we've got T1 sine 60 plus T2 sine 45 equals 6g, or 6 times 9.8. Therefore, root 3 over 2 T1 plus root 2 over 2 T2 equals 6g. If you look, we know that root 2 over 2 T2 is the same as a half of T1. So therefore, I'm just going to pop that root 3 over 2 T1 plus a half of T1 equals 6g. You can pull out T1 as if it's a common factor, so you get root 3 over 2 plus a half equals 6g. Pop that in your calculator, okay, and you get that T1 equals 43.04 newtons, which of course is 43 newtons to two significant figures. Then you can put that back into this statement here. You can see, right, that a half of T1 equals root 2 over 2 T2. So therefore T2 must equal T1 divided by root 2. So just rearrange that. Therefore T2 comes out as 30.4 newtons, or 30 newtons to two significant figures. And that is the end of this first video.